The title of our report is Aspect Level Sentiment Classification with Unbiased Attention and Target Enhanced Representations. My name is Liu Peng from Institute of Information Engineering, Chinese Academy of Sciences, Beijing, China. This is our outline, which includes introduction, problem, our approach, experiment, case study, and conclusion. As a fine-grained classification task, aspect level sentiment classification aims at inferring the sentiment polarities of opinion targets for a given sentence. A sentence might contain multiple sentiment target pairs. We give an example in the table 1. The given opinion targets are food and service. Our goal is to predict their sentiment polarities, which are positive and negative respectively. The main challenge of this task is to extract relative information concerning the given target entity. We believe that there are two ways to overcome this challenge. One is to apply the attention mechanism, which has shown to be effective in previous state-of-art models. The other is to learn context representations based on relevance to the opinion target. Our work starts from the above two aspects. Despite the attention mechanism has brought significant improvements to aspect-level sentiment classification, there still exists a problem. That is, sentiment words tend to get more attention, despite the fact that they may be irrelevant to target entities. We call this as attention bias problem. As shown in the second sentence of the figure, the target word is drink and its real sentiment polarity is neutral. However, the sentiment word friendly tends to get surprising high attention, which may induce the model to output positive polarity. In addition to the attention bias problem, we also found that a sentence sometimes contains multiple opinion targets, the context of which may express different sentiment information. For example, in the sentence, "Great food, but the service was dreadful," there exists different sentiment polarity toward food and service. When judging the sentiment polarity about service, we hope that the sentiment information irrelevant to the target can be filtered. Our approach focuses on solving the two problems mentioned above. The first one is attention bias problem. Attention is calculated based on the sequence of all embeddings. Most attention-based models used to feed the sequence of or embeddings into a bidirectional long short-term memory, namely bi-LSTM layer. Then, attention weights are computed based on the hidden states of the targets and other words. Intuitively, if the word sequence has low preference for sentiment polarity, attention may not be biased to sentiment words. Based on this idea, we consider removing sentiment information from the word embedding layer. Thus, we design a sentiment discriminator. The discriminator is used to classify sentiment polarity of the word embedding layer. The discriminator learns its parameters by maximizing its classification accuracy. The loss function of the sentiment discriminator minimizes the negative log probability of the sentiment label. On the contrary, the word embedding layer for attention is optimized to confuse the discriminator to minimize its accuracy. Thus, we design a adversarial loss function based on the KL divergence. The KL function has two inputs, Q and P. Q represents the probability distribution which is outputted by the discriminator. P is the uniform distribution. According to the characteristics of the KL function, Q will be close to uniform distribution when the adversarial loss function becomes small, which means that the odd embedding layer for attention has low preference for sentiment polarity. In the wake of convergence of adversarial training process, the discriminator will fail to distinguish sentiment polarity of the odd embedding layer, which means that different sentiment polarities of words lies in a similar region in embedding space, and sentiment information has been discarded. The process is shown in the figure on the right. As the adversarial loss function is optimized, the discriminator will misclassify sentiment polarity of the odd embedding layer. This is because different sentiment polarity of words lies in a similar region in embedding space. However, similar odd embeddings may make context words be similar to each other. Attention weights of different context words will become similar. To ensure diversified distribution for attention weights, we minimize the regularization term to enforce the uniqueness. As shown in the equation, P represents the distribution of attention. HP is the entropy of P. As entropy decreases, P will deviate from the uniform distribution. Based on this loss function, our attention weights, where loss becomes similar to uniform distribution. In addition to use adversarial methods to optimize attention weights, we also propose an embedding preserving gating mechanism to learn word representations. The gating mechanism is used to control the path through which information flows in a network and has proven to be useful for the RNN network. We use the gating mechanism to incorporate target-related information into the word representations dynamically. Gated 10 units, namely GTU, which is one of the effective gating units, is chosen in our model. The gating mechanism acts on contextualized feature (HRI). It may discard some original old information which might be useful for sentiment classification. To alleviate this problem, we try to incorporate original word embedding (ERI) and propose an embedding preserving mechanism which which conducts a concatenation operation similar to the residual collection between GRI and ERI. The overall architecture of our model is shown in the figure on the right. To combine the results of word representation and attention weight, we use the thin layer. The sentiment polarity of targets is usually determined by some key phrases. We choose thin layer as our classifier as it's useful for extracting n-gram features. We conduct experiments on two datasets. REST-14 from SimEval 2014, Task 4, and REST-15 from SimEval 2015, Task 12. These datasets contain a lot of user reviews, and each review associates with a list of opinion targets and corresponding sentiment polarities. The statistic of datasets is shown in the table 2. To evaluate the effectiveness of our method, a model is compared with many strong baselines. To investigate the impact of the impinging mechanism and unbiased attention independently, we develop other ablated models. One is LSTM plus adversarial attention plus CNN, and the other is LSTM plus the common attention plus epigating plus CNN. As shown in the table, our model can Our model can benefit from unbiased attention and the gating mechanism, and the full model achieves the best rest on both accuracy and macro F1 score for the two datasets. In order to understand how unbiased attention contributes to the model's performance, we pick some test examples. Figure 4 shows the visualized attention results. For the sentence in Figure 4a, the staff members are extremely friendly and even replaced my drink once when I dropped it outside. The target word is drink. However, the common attention model worth assigns a relatively high weight to the sentiment word friendly, which actually is used to modify the opinion target staff. Eventually, this sentence is misclassified as positive polarity and shown in the Fig 4a. The problem is corrected in the adversarial attention model, which shows that the adversarial method is useful. In conclusion, we propose two mechanisms, namely unbiased attention and the impinging mechanism. First, to make the attention focus on the really crucial part for the target, a novel adversarial training method is used to get unbiased attention. Second, we propose an impinging mechanism to learn target real-world representations. Finally, experimental results on two benchmark datasets from the semi-inverse tasks demonstrate the effectiveness of unbiased attention and the impinging mechanism. At last, if you have any question, you can send the email to me. Thank you. Thank you all.